We're continuing our discussion of the magnetic lift. In part E, define the potential energy U of H that is 0 when H is equal to 0. What is the potential energy for H between 0 and R and for H greater than R less than H top in part F? All right, so we're going to make sure that the potential energy is defined to be 0 when H is equal to 0, and we want to know the potential energy for H between 0 and R. Now the potential energy basically has a contribution from the magnetic field, which is minus mu dot product with the magnetic field. That is minus 2RWNIB cosine of the angle between them. So this scenario is what we did in part C. The angle between mu and B in this case was pi minus theta. So it is cosine of pi minus theta. And what is cosine of pi minus theta? Cosine of pi minus theta is cosine pi cosine theta plus sine pi sine theta, and sine pi is equal to 0. So cosine pi is minus 1, so this is minus cosine theta. That's the cosine pi minus theta. So for the magnetic potential energy UB here, with this minus sign and the minus sign coming from this, I'm going to have 2NI RW B cosine theta. And what was cosine theta? According to this figure, it is R minus H divided by R. So this is 2 RWNI R minus H divided by R, and the R's cancel. So I find that the potential energy, the magnetic potential energy, is mg sigma R minus H. Why? Because 2WNI times B, I have forgotten the B here. 2WNI times B is mg times sigma. So this is mg times sigma R minus H. Now, what is the value of this when H is equal to 0? What is the value of the potential energy when H is equal to 0? Magnetic potential energy. If you substitute H equals 0 here, you will get mg sigma R. So mg sigma R, which is equal to mu times B actually. So redefining my potential energy with respect to H equals to 0, UB prime, new definition, it is mg sigma capital R minus mg sigma capital H, that's this potential energy, minus the potential energy at 0, UB at H is equal to 0, and that is equal to mg sigma R. So this new potential energy now becomes minus mg sigma H, because this and this will cancel when I put it here, and I will get minus mg sigma H. And so that I make sure that the potential energy is defined such that when H is equal to 0, it is 0. Because the gravitational potential energy is already 0 at H is equal to 0, this was necessary so that the total potential energy becomes the shifted potential energy for the magnetic portion plus the gravitational portion, which is mgh. Mgh is the gravitational potential energy minus mg sigma h. The total potential energy becomes mgh 1 minus sigma. mgh 1 minus sigma. Okay, so let's do the same exercise in part F when h is greater than r. The magnetic potential energy is minus mu dot product with magnetic field. So that is minus 2rw NIB cosine of the angle between them. That was done in part D, this scenario. Cosine of the angle between them is cosine beta. Okay, so that's cosine beta. And beta was equal to pi over 2 minus alpha. So that's cosine pi over 2 minus alpha, which we have shown before. Let's do it again. Cosine pi over 2 cosine alpha plus sine pi over 2 sine alpha. Because this is 0, that disappears. We obtain sine alpha. So this potential energy is minus 2rw NIB sine of alpha, and that is minus 2rw NIB sine alpha is sine of h minus r over r, because we have shown that h is equal to r alpha plus r in part D. So that the total potential energy becomes now mgh plus the potential energy ub that I have calculated minus its value when h is equal to 0 minus mu b. So this gives me mgh minus, for 2rw NIB, I have sigma times mgr, so minus mgr sigma sine of h minus r over r minus mg sigma r. That's the value of the potential when h is equal to 0. That's my reference point for the potential energy. So this total potential energy now becomes mgr. It is h divided by r minus sigma sine of h over r minus 1 plus 1. So you can see here it is mg sigma r, that's this one, minus mg sigma r sine, that's this term, and mgh is the first term. So that's my total potential energy, which is valid for h between r and h top. So this is for r, h top. That's the potential energy. So now in part G, if sigma is greater than 1, for what value of h will the mass remain suspended motionless? Okay, so sigma is greater than 1. We are requiring it to be motionless so that the net torque has to be 0 for the mass to remain motionless. And for h between 0 and r, the net torque we have calculated was h 2r minus h square root mg 1 minus sigma I hat. So let's check this. This is from part C. So in this scenario, you calculated this torque, and this should be equal to 0. It will be 0 when h is equal to 0 or h is equal to 2r. Now h cannot be equal to 2r. The maximum value of h is h top. So h is equal to 0 is a solution. Because this is valid for h between 0 and r. So this torque is valid for h between 0 and r, so h cannot be equal to 2r. What about h between r and h top? The net torque we calculated in part D was mgr 1 minus sigma cosine of h over capital R minus 1 in I hat direction. This should be equal to 0. And that implies 1 must be equal to sigma cosine h over R minus 1, and cosine inverse of 1 over sigma is equal to h over R minus 1, and this will give me sigma has to be greater than 1 here. You can see for this to work, because cosine is a function that varies between minus 1 and plus 1, and therefore h will be equal to R times 1 plus cosine inverse of 1 over sigma. So under this condition, it will remain motionless. So either for h is equal to 0 or h is equal to this value. Now let's look at the last part of the problem. For what values of sigma will the cylinder rotate more than 180 degrees if the mass is released at top? So that means there will be a positive potential energy on top. Okay, now I'm looking at the potential energy I know was defined to be 0 at h is equal to 0. So when the potential energy on top is greater than the potential energy at the bottom, it will rotate. So it will rotate more than 180 degrees to reduce the potential energy. What was the potential energy for R, H top? So H between R and H top. This is the potential energy we calculated in part F. It is mg R H over R minus sigma sine of H over R minus 1 plus 1. And H top, we're evaluating this at H equals H top. H top is capital R times 1 plus pi over 2 we have found in part B. So H top divided by capital R is 1 plus pi over 2. So the potential energy evaluated at H top, H equals H top, will be equal to mgr. H divided by R is 1 plus pi over 2 minus sigma sine of pi over 2. 1 plus pi over 2 minus 1, that's sine of pi over 2, plus 1. And the potential energy at H top will then be equal to mgr 1 plus pi over 2 minus 2 sigma, because sine pi over 2 is 1, 1 plus 1 is 2, minus 2 sigma. And this has to be positive, which means that sigma should be less than 1 over 2 this is 1 plus pi over 2 minus 2 sigma, 1 over 2 plus pi over 4. If this condition is satisfied, if sigma is less than 1 over 2 plus pi over 4, then it will rotate past the 180 degrees. Okay, so in this part of the problem, I have calculated the potential energy, assuming that the total potential energy is 0 for H equals 0. The potential energy has two contributions, magnetic contribution minus mu dot B, and the gravitational contribution mgh. This is already 0 when H is equal to 0. If you look at minus mu dot B, and remember that this is valid between 0 and r, it's the magnitude of mu times magnitude of b cosine of the angle between them, cosine of pi minus theta, which we have shown to be minus cosine theta. This potential energy turns out to be mg sigma r minus h. If you look at h equals 0 value, it is non-zero, mg sigma r. So that value should be subtracted to redefine the energy. So the redefined magnetic potential energy, EUB prime, is this value minus mg sigma r, which is minus mg sigma h. That's only this portion. So the total potential energy becomes gravitational potential energy mgh plus the magnetic potential energy minus mg sigma h. That's the value we find here. For part F, if h is between r and h top, now we have the new angle beta between mu and b, where beta is pi over 2 minus alpha. Cosine of this angle beta is sine of the angle alpha, which we have shown to be equal to where we have shown that alpha is h is equal h minus capital R over R, or h equals R alpha plus R. We have substituted that here. The total energy is mgh plus this potential energy minus the potential energy for h equals 0, which is minus mu b. So that's basically how we define the magnetic potential energy. So this total potential energy has now this value, which is valid between h equals r and h equals less or equal h top, or greater or equal r. Greater or equal r. Okay. So if sigma is greater than 1, for what value of h does the mass remain motionless? For h between 0 and r, there are two solutions, h equals 0 and h equals 2r, for the net torque equals 0. The answer we have copied from part C, but h equals 2r is not possible because this is not valid for h greater than r, so this answer is not correct. So the only answer is h equals 0. If h is between r and h top, then this net torque should be equal to 0, which tells me that h equals r times 1 plus cosine inverse 1 over sigma, implying that sigma has to be greater than 1, as suggested in the problem statement. Provided that sigma is greater than 1, this is a solution. And in part H, if we release the object on h equals h top, will it rotate more than 180 degrees? It will if the potential energy is greater than the potential energy at h equals 0, so that it will minimize its potential energy by rotating. And we looked at the potential energy expression for h equals h top, basically looking at our answer from part F and setting h equals h top, where h top over r is 1 plus pi over 2. That's the answer from part B. So we can calculate the total potential energy like this. And in that case, this has to be greater than 0 because the potential energy was 0 for h equals 0. So sigma has to be less than 1/2 plus pi over 4 for it to continue rotating after reaching 180 degrees.